Okay, so in the previous class, mathematically and through Simulink that I shared with you the file, we said that for this marginal stable system that can be any system, y over x, and the example was the pendulum problem, right? Like omega n square, s square plus omega n square. Why marginally stable system? Because the roots of the denominator, which is poles, as I told you, the roots, we name it poles. We have two poles, S1 and S2, and this is equal to 0. Is pure imaginary poles, a pair of pure imaginary poles. Means that if you want to play, I explained previously in the previous classes, if you look at your notes, in complex plane, if this is imaginary axis, you have this, I'm just refreshing your mind, and this is real. You have a pair of pure imaginary poles. So if you remember, I taught you that with any input to the system, if you want to plot y over t, you're going to see a harmonic because it's a marginal stable system. So I said that x of t, if you remember, refreshing one because we're continuing, it's going to be delta t minus t naught, means the delayed impulse. Let me write it clearly. And you saw that we got, after applying the Laplace, if you remember from previous class, as an inverse Laplace, we got the y of t, we got was sine t minus t naught. Meaning that, as you saw in the Simulink, I'm going to open Simulink because we're going to continue Simulink and math today again. So it was this delayed impulse as the input. Here we go. And here is t naught. As you saw in the Simulink and in math, I showed you. So the output is going to be this. So it doesn't change anything because your system by itself has two imaginary poles. Also, I said if you have a input of the system, and this is closed loop transfer function, remember that? Is a delayed step input, unit step input. We got that y of t was again, oh, we plotted that actually. I'm going to drive it today. So we got that y of t, if you want a y over t, so this is delayed input, as you saw in the Simulink file I shared with you. Here's t naught, and here's 1 unit step. This is input. The output was again what? Here we go. Because still you're working on this system that has a pair of pure complex poles of the system. So you're gonna, okay. Can I go to the next page? Guys? Yes?
Sure.
Okay, so y over x, I'm just writing here, guys, is omega n square s square plus omega n square. Remember, for the Simulink example, I said omega n is 1 radian per second. Okay, so when x is delayed unit step, means if you apply Laplace to both sides, Laplace, this is x of t, x of s, based on what the rules I taught you gave in notes, going to be e minus t naught s divided by s, because Laplace of, if you look at your notes, unit step is 1 over s, with the delay, that's right, gonna be minus t naught. So having that here, you get that y of s, mathematically, I want to show the proof, and then I'm gonna jump to other things. Gonna be e minus t naught s omega n square over s square plus omega n square. What we want to find, the intention, what we derived through Simulink, I plotted to you by the block diagram, closed loop unity feedback block diagram. I want to see mathematics proving this graph. Okay. So what you're gonna do, you're gonna say from high school, you have to put you have to write like this: e minus t naught s, and you can decompose to this: a over s plus b over, because the roots, the poles of these are, as I said, s is plus I omega n, and s2 is minus I omega n. These are the poles of the system for this part. Okay, so it's gonna be s minus I omega n plus b plus c. We are decomposing to, okay, and c s plus I omega n. This is how we do this, right, from high school. Then I'm gonna contribute e minus t naught s in each of them. Okay guys, now what I'm gonna do, for God's sake, as I did in the previous class, inverse Laplace. So, sorry guys, this is s. So y of t, finally, gonna be, because from s to t, right? From s to t, gonna be omega n squared. I don't care about the constant a, b, and c. You know that. You have seen this. Here we go. So this comes from delayed input, delayed this. So you're gonna have some a delayed t minus t naught. That's right. Yes. And remember, Laplace of e minus plus minus at is 1 over s minus plus a. Exactly the same. So what delayed that? Delayed, right? So you're gonna have here b e, because this is minus, gonna be plus I omega n, but delayed t minus t naught, plus c, and here's plus, gonna be minus I omega n t minus t naught. Using the Euler equation I told you, remember that you had in your notes, e plus I theta is cosine theta plus minus I sine theta. This I, this I, this I. That's right. So you see that it is gonna be eventually omega n squared a t minus t naught, and I'm skipping the math because I have done this previously. That's right. You're gonna get some d sine omega n t minus t naught minus some phase angle. So this come from here. This, and has a delay, happens here, delay, right? So I want to take you back to Simulink 5 that we developed together. What was that? Oh, here we go. Okay, you received that, that's right. I sent by email to everyone. Yes? Yes, everyone? You got it?
Yes.
Good. So let's see. Open this, open model. Okay. So it's coming up. Let me pause this. So you saw that this is and remember that we had no continuous time impulse. We differentiate it from step input that gives you what? Gives you impulse. That's right. We plot it here, and then delay. And your friend said 3 seconds. I'm just running because I want to expand this Simulink file. Okay. Here we go. So you see that. Come on. Oh, okay. See that this is the impulse. We created from the step, and then this is the sign. You see that. And when you go to a delayed unity step, and we create it by putting a step time 3 here. Okay. And here we go. See that? And this is the unity step and oscillation. See what I'm saying? I have to just fix the graph in the notes because that looks a little offset. So because this is your sine, you saw in the Simulink plot, plus the unit, so we have to shift it up actually. So this must be like this. Yeah, here we go. Right? Mathematics says is sine, as we derive together today, is sine plus this, so we have to shift it up. Okay, understand? I'm gonna back there, but before going there, I have to just write something here. Can I go to the next page? Everyone? Yes? Can I? Okay. So remember that I said Simulink had no what? Continuous impulse. So we differentiated by s plus 0 over 0.1 s plus 1. This is almost s. S means derivative. That's right. I taught you it several times. This gives you what? This gives you continuous time impulse. Here we go. Right? Now, the third input that I promised you, so we did impulse step, and now says this third input is ramp t. You know that the x of s, based on whatever I taught you, is 1 over s squared. And so y gonna be 1 over, based on the example, s squared plus 1. From here, guys. Put here x, and I set omega n, this is example, is 1. So we want to see how it looks like. So before going there, can you guess what's gonna be t? based on whatever I taught today. Because system dynamics by itself didn't change. So what to expect to see, guys? What to expect to see again? Huh? This is input to the system, ramp. So what to expect to see again as output? Based on whatever I taught. You have two pure imaginary poles. What to expect to see again? Tell me. Yes, because nothing changed. So your system by itself is marginally stable. It means it's gonna oscillate forever. So I'm gonna push the button of the control and negative to make it small. Positive, make it large. Okay. So what I'm gonna do, I'm gonna just copy and paste. Okay, and make it smaller. Copy paste here. Okay, and I'll make it bigger. So what if you want to go here? Just say ramp. Here we go. We do have ramp. We do have. So drag it here. Okay. And then delete this. But I want to have the delayed ramp. So slope is 1, means 45 degree. Start time, give me a delay. Just 4 seconds, huh? 4 seconds. It's a delay. Apply, going. And this is open loop G, open loop transfer function. Okay, 1 over s squared. Again, I'm emphasizing million times. In the feedback control, never put the closed loop transfer function. You have to put open, G. Okay? So if I run this, as your friend said, because system didn't change, okay? You see that. There we go. This is delayed input for 3 seconds or 4 seconds. I don't remember. The output is oscillation, forever oscillation, because system is marginally stable. Okay, so the output doesn't follow input. You have an error signal here, error signal here, error signal here, error signal here. An error signal obviously gonna be oscillatory. There we go, as you see. Again, like that. See what I'm saying? Yes, nothing changed. Now, the fourth input I promised you was parabolic. You can look at your notes. Parabolic. If you type, we don't have such an input in the Simulink, like impulse. So we have to use some trick. Okay, how? Let me take it back to what? The notes. So you saw that this is input, so this is output. Actually, for this, for the Simulink, I said x of t was t minus t naught. Okay, so you know that I taught you with the delay, x of s is 1 over e minus t naught s squared. All right, come on. Okay, and if you want to plot that, as you saw in the Simulink, put it together. If this is input, here we go, 45 degree. Here is t naught. You saw the output, because system is marginally stable, gonna oscillate. You saw it, that's right. So, I have to open a new PowerPoint file. Okay, so fourth, I told you it's x of t is parabolic. I don't want to put delay because I taught you delay. Okay, so you know that the x of s, you have your notes, is 1 over s cubed. Okay, so again, what to expect to see, guys? Tell me. What to expect to see? What kind of, this is parabolic input to the system. What gonna be output? Tell me. What's gonna be output? You're gonna say this. Okay. But we don't have it, guys. In the Simulink, we don't have it. Y over x is 1 over s squared plus 1. We don't have 1 over s cubed in the Simulink. We do not have it. So I'm gonna do a trick. I'm gonna say if this is 1 over s squared is 1 over s squared plus 1. This is what input to the system? Look at your notes. I just told you. Which input to the system it is? Guys? Which input? No. Which input to the system is? Which input to the system is? Well, which input to the system is? What is this? This is from ramp. Yeah. Guys, this is from middle school. Not even high school. Okay. So, this is, this is ramp. This is ramp. We do have ramp in the Simulink, right? Now I'm gonna play with this. How? I'm gonna say, you know what? I add a s here and make this like that. It's gonna be the same as, right? Everybody agree? Yes or no? Yes? You got it? This is equal to 1 over s squared plus 1. Now I'm gonna move the s here. So you get y is 1 over s cubed is s squared plus 1. Everybody agree? Not magic, just plain. Okay. Now what is this? What is this? Huh? What is this? What is this? I just taught you. Parabolic. So this is parabolic. But I changed the closed loop transfer function. So I have to find new open loop transfer function. Until this point, closed loop transfer function was this, s squared plus 1. I changed it. So I have to change the open loop transfer function. You get what I'm talking about, everybody? Yes? So let's find it together. This multiplied by this multiplied by this. S1 plus G is G S squared plus 1. S plus SG is G S squared plus 1. So G gonna be S squared minus S plus 1 equal to S. So the open loop transfer function you have to use in the Simulink gonna be 1 over S squared minus S plus 1. So in this case, what was the open loop transfer function? Was this, look at here. Now I changed it for the parabolic. You see what I'm talking about, everybody? Yes? Clear, everybody? Hmm? Okay, so I have to change it. What I'm gonna do, this is, oh, this is second order system. So your numerator, as you saw in the Simulink, gonna be 0, 0, 1. Here we go. And denominator gonna be 1, minus 1, and 1. I have to introduce in the to change it, guys. Okay, let's do that together. So I'm gonna copy and paste this. Take this down. I'm gonna keep this with not delayed, starting at 0. Okay, because delay is enough. You learn that. Okay. Okay. Oh. Okay. Okay. So as we did, this is just again this, and now I have to change this open loop transfer function. 0, 0, 1. It was minus 1 and 1. Look at here. Here we go. 1 minus 1 1. So this is gonna be like that. That's right. So apply. See, changed. Now if I run this, I expect to see parabolic. Oh, what happened? Hold on. Let me fix this first. I see now. Because I'm driving with you. Oh, this is, yeah, this is S. See, S. So the numerator gonna be 1 and 0. Here we go. S. You got it, everybody? The mistake was here. Here is 1. 1 minus 1, 1. S square, S square. Yeah. So this is gonna be 0, 1, 0. 0 S square plus S plus 0. Like this one. 0, 1, 0. 0, 1, 0, yeah. So let me fix that. 0, 1, 0. And here we go. Oh, I have to first save it. And here we go. So this is, oh, this is too much. Let me take you, I don't know, 2 seconds. So this is parabolic. Okay, the yellow one. Oh, I don't have to compare this with this. This is funny. Okay, this is parabolic. What's going on? hold on. So now I can compare with that. So this is okay, go ahead. So I added an integrator here to make it 1 over s cubed. See here, ramp to 1 over s squared, and 1 over s is 1 over s cubed. So it's gonna be parabolic. So now let's compare with the output. See what I'm saying? And now we can compare them. So like say 10 seconds. Okay. Okay. Here we go. So this is the input, and you see the output is again what? Again sine. Here we go. And this is a 25. There we go. There we go. This is sine. And they have a huge error. System is again sine because it's a pair of pure imaginary poles. And there's a huge offset between them. Okay? So this is how we work in 4 different inputs that I promised you. You got it, everyone? Yes? So you're gonna tell me why, Periman, you taught us delay. Because if you go to my lab website, okay, we did experimental and analytical approach for robotics problems. And we had many publications with my PhD students and my collaborator, famous collaborator, Professor Miroslav Kirsic at UCSD, about delay control of robotic system in my lab. I have 7 degree of freedom robots. Let me show you one of them. Yeah, in Automatica we published in 2019, and I got an interview for that by KPBS News, and I want to show the paper for you. This is very high level, but I'm just exposing you when you go to industry, see the delay in the system, what I mean. Feedback generalization based predictor for time delay control of a high degree of freedom robot manipulator. Okay, this is very high level control, not in the your undergraduate level, but this is the robot in my lab. I'm going to show the video right now to you how to design compensator if you have delay. Here we had delay in the actuators, not in the input of the system. I show. Let me emphasize here, guys. Here you had delay in the input of the system. Okay. Let me expose this to you. Remember, I showed you in the previous class. Only showed to you. I didn't teach you. If you put PID controller, I'm going to teach you in this semester. Okay, here we go. And if you tune it, don't ask me why. Integrator is 0, and here going to be set for derivative PID. Now I'm going to tell you why I'm teaching you this. Okay, if I run this, remember from previous class? You see the output follows the input by putting the PID controller, even with the input delay. Okay. Now, if I look at, guys, if I put the delay in after controller here, okay, in actuator, this is actuator. Controller means actuator in robotic systems. Where is that? We have the motor here, motor here, motor here, motor here. So we assume that there is an actuation delay in controller delay. Okay. So if I run this again after actuator, okay, see what you're gonna see. See, system becomes unstable, guys. Blew up. Goes to how much? 10 to the power of 6. And this is linear system I taught you. For nonlinear robots, okay, we have to design compensator predictor to compensate that delay and make the system stable. Very, very high level paper that we did it. My graduated PhD student Mustafa Baghri, now he's a senior engineer at Johnson & Johnson, and this is my collaborator, Professor Kirsic. So let me show the video to you to see what's the application of what I'm talking about. Let me delete this because I don't wanna. Oh, what happened? Yes, I'm gonna share the file with you. What the hell is happening? Sorry, guys. Yeah? Okay. So let me run the video to see what's the application of that. Take a look at this, guys. There we go. Guys, did you see that the robot failed? Did you see that? Huh? Everybody? Yeah. That's exactly when I showed the PID, and after PID I put the delay. That the graph went to 10 to the power of 6. Exactly that is, okay? Not in the robotic system, in the very simple linear system, but I wanted to visualize what's happening, okay? I'm talking about here. Look at here. See? Here. See? Robot fails here. What's that? So to pick up the item and override the obstacle and put on the green pad as destination, okay? But exactly what happened is I'm simplifying it on the graduate level for you, okay? Exactly happened, I'm going to show it again because this is very important. When you go to industry as a graduate of the CSU, even guys, if you, the rover on the Mars, okay, because we have no access on that, okay, so maybe there is an actuation delay. So the engineers from the Earth, they had to fix this by putting the predictor that you saw the paper that we published, okay. So if you put the delay here after actuate, oh my God. If you put the, here we go, okay. Oh, sorry. What's happening? Okay. Yeah. So today I don't know what's happening to my cursor. Okay. See, I'm going to send this to you because I taught you here today. So we have to, after here, guys, after here, I'm putting here. We have to put the predictor in the paper that I told you to fix this delay that coming out of the actuator. Control means actuator of the motors in the robotic system. Okay? See what I'm saying? So let me fix this thing. Okay, so if I run this, see that huge divergence going up to 10 power of 4? Exactly the visualization of this is that when the robot failed, okay, picked up the item but couldn't go override the offset and put on the green destination. So if you want to fix it, you have to design delay compensator or predictor. See what I'm saying, everybody? That's why I expose you to the delay. When you go to industry, many times, even that maybe you have sensor delay. Here, this is feedback, that's right, unity feedback. But I told you sometimes we have a sensor here. Maybe in sensing you have delay. If that happens, again your system fails. You have to fix it. See what I'm saying, everybody? So let's continue the video. Okay, everybody? So I'm gonna send this. Actually, I want to delete this because this is not good. I didn't teach you yet the PID. I just wanted to give you the sense of what does it mean. Okay, here we go. Okay, so we are done. I'm gonna share again this with you. But sometimes coding in MATLAB for the control is easier than the Simulink. Let's go for it. Oh, first of all, I have to fix some graph here. Where's that? Oh yeah, this graph must be like this. I don't know why mistakenly you plotted like that. As you saw, this is input, so this is output. Okay, again, that's right. So now coding of this in MATLAB. I told you that the close the transfer function. Now forget about the delay. We don't have delay. We have just normal operation. S squared plus 1. A marginal stable system. Because you have a pair of pure complex poles of the system. Okay. So if 1, x of s is 1, means impulse. Okay. So from here, y gonna be 1 over s squared plus 1. The problem is that in MATLAB coding, we do not have impulse command. Okay, what we have to do is easy peasy. Look at here. We're gonna say y is over 1 is equal to 1 over s squared plus 1. Now you're gonna say 1 is s in 1 over s squared plus 1, because 1 s is gonna be 1, that's right. What is this, guys? I taught you. Look at your notes. Which input is this? Which input? Which input is this? I'm writing here. Which input is this? Unit step.
Step.
Exactly. So if you say y over unit step, and s goes up here, s squared plus 1. So it's enough. I'm gonna type the command. We say num second order system gonna be 0 1 0, because it's 0 s squared plus s plus 0. Here then you're gonna have to say it like this, then denominator gonna be 1, 0, 1, because you are missing a S here between. Okay, I'm gonna type it in. So then you're gonna type step num then. This gonna gives you impulse input. You change everything. So let's try together. And also I'm gonna share the MATLAB file with you. So you open a MATLAB file, okay, and you say, first of all, clear all. Always do that. You say num is 0, 1, 0, as we said. Then is 1, 0, and 1. Right? Look at here. Yeah. 0, 1, 0, 1, 0, 1. Then if you MATLAB knows this command, step num and then. This is close the transfer function. I'm writing here, guys. I'm saying when using step command, you have to define num and, sorry guys, num and then of closed loop transfer function, because I'm going to share with you this code. This is inputs coding, I'm saying, I'm sharing with you. Okay, now let me run it for you. Here we go. See, margin stable system, sign, all of that. If I remember correctly, you can define time frame. Time is between 0 and 0.0 to, I don't know, 10 seconds. I forgot that because time. Okay, you can put time here, hopefully. Yeah, there we go. For time seconds. Do you see that, guys? Everyone? 10 seconds. And we saw that for the impulse input, because your system is margin stable, gonna be oscillation. You can increase to 20, say. Here we go. There we go. Obviously, you can grid that. And you can do whatever you want. Okay? There we go. Amplitude, time. This is impulse. So let me say, because I'm going to share with you, I'm saying impulse, num of impulse, then of impulse, num of impulse, then of impulse. Now let me go back to the next one, encoding. Can I? Everybody? So, 2. When x of s input to the system is 1 over s means step, as now we know. So you don't not change anything here because we have a step. So y over step, we have it in MATLAB. So it's gonna be s squared plus 1. So you have to change the closed loop transfer function as num as 0, 0, 1, and then as 1, 0, 1. See, compare these two. We played for the impulse, but we do have a step. Okay, so I have to change that only. Let me go back to that beautiful MATLAB. So I'm gonna say copying and pasting. So this is gonna be for unit step. Here gonna be 0. Only I'm changing this. Here we go. Then I'm gonna do this step and time. Again, we expect what? Sine, harmonic. Oh, because I have two graphs. Figure 1 and the figure 2. Or, you know what? I'm gonna plot all of that together. I'm gonna see this is, hold on. Let me see if it works. I'm gonna put the impulse with the step together, huh? Let me see if it works. Yeah, it works. It's good. Actually, give us a, to make that happens. I'm gonna compare them. It's a good idea. So I'm gonna say legend. The first one is for impulse. The second one is for step. Okay, it's good. So you see, for the marginally stable system, like as a pendulum, here we go. The blue one is for impulse response, step is for step response. But step goes to, must goes to 1 and impulse 0, but it's marginally stable system. Now, let's go for ramp. Can I, guys? And I'm gonna assign this, the last one, to you as your own homework. So, new 3. If x of s is ramp, 1 over s squared. We don't have ramp. We don't have ramp. So what I'm gonna do, I'm gonna stick again to this step response because we do have it. I'm gonna play with that. I'm gonna say, you know what? I'm gonna put one s here, and one s here, and one s here. It kind of gives you the same. 1 over s squared plus 1. This s goes up here. So you get y equal to 1 over s squared. This is ramp. This is ramp now. It's gonna be s squared plus 1. So only you have to change num as right, hold on. See, the new version of the MATLAB has ramp. Let me first try it. Okay. So let's go back here. Okay. I have to fix this. Come on. Okay. So this is step, so ramp. So what I'm gonna do, I'm gonna say, okay, this is one. Now I see that is 1 over s, 1 over s. Now this is ramp, this is step. So I'm gonna move this here. I'm gonna move this here. Here we go. If I do that, it's gonna be step, because we have a step command. And let me delete this. Okay. And it's gonna be this time s in s plus 1. And here is 1. So your num gonna be, okay guys, look at here. 1 over s cube plus S. So your num must be third order because the highest order is 3. So you're gonna have num. What's happening, guys? Num is 0, 0, 0, 1. Then is 1. There's no S square. Oh my god. 1. There's no S square. 0. S 0. This is how we play with that. You got it, everyone? Yes? Everybody? You got it how I did it? I changed it to a step. So, if you do that in MATLAB coding, I'm gonna say here gonna be ramp, third order system, and this is like that, exactly as I typed in the MATLAB. Here, 1, 0, 1, 0, 0, 0, 0, 1. Okay. Now I can say, hold on. Okay. And then this is ramp, ramp, ramp. There we go. And this is for ramp. If I run it, here we go. See, we saw in the Simulink. Remember, guys, in the Simulink, this is for ramp. Did you see it? Everybody? Yes? Good. Now do whatever I have done. And let me say this as a red. I'm not sure if I can do that, but I try my best. Blue and green. Or maybe I have to define the color command. Yes, I think so. Let me see. Color. I think we have to write like this. Color and color. Oh. Maybe it doesn't accept color. I don't want to challenge myself now for this. Okay. Okay. So now we have it like that. Now do whatever I have done and go for yourself. When I'm sharing this code, go for input of the parabolic. Change with this and see what you get number and denominator. You got it, everyone? Okay. So